Okay, so we left off yesterday, we had talked about work, okay, and work was dependent on how much force was exerted and over what distance it was exerted. We talked about potential energy, okay, which was mass times gravity times height. We talked about how work is a change in energy. So anything that results in a change in either potential or kinetic energy, okay, is going to require work. Those are the things we covered yesterday. And we ended off talking about kinetic energy, right, which is energy due to movement. You have kinetic energy if you are moving. Okay? Now, at the end of class, we had just gotten a look at the formula for that. Okay? And that is that EK equals 1/2 mv squared. Which means kinetic energy is dependent on two things, mass and speed. So the bigger something is, the more kinetic energy it can have. And how fast an object is moving, the more kinetic energy it would have. However, the thing we have to understand is an increase in mass does not have the same effect as an increase in speed on kinetic energy. Okay? And the reason for that is, in this formula, v is squared. So that means any change in speed results in an exponential change in the amount of kinetic energy. Okay? Did I go over the whole like, stopping in a school zone, going different speeds thing with you guys? Okay, with my physics kids I ranted with. Now I'm going to rant with you. Okay? So, here's what we need to know. According to work energy theorem that we covered yesterday, any change in energy is going to require work. If I want to stop, I'm in motion and I want to stop. The only way I can stop is to get rid of my kinetic energy. Now, when I apply the brakes in a car, what do the brakes do? Obviously they stop. How do they do that? Okay, has anyone ever seen what happens when you apply your brakes? Okay, so in your car you've got a rotor, it's the silver thing you can see through your wheels, okay, and on there are calipers. Okay, the interaction between those two things is what causes your car to stop. When you press the brake pedal, the calipers squeeze against the rotor. Okay, when you squeeze metal together, what happens?
Get a lot of heat.
Yeah, you get a lot of heat because there's a lot of friction in there. Your brakes rely on friction to stop your car. And what friction does is it turns kinetic energy, or mechanical energy, into heat and sound and light sometimes. Okay? So it changes the amount of energy that is kinetic into other things, which is going to result in you slowing down and then hopefully coming to a stop. Everyone kind of follow on that? Okay, so that's how brakes work. Now, obviously there also has to be friction between your tires and the road, right? Because in the wintertime you can slam on the brakes, clamp those calipers against the rotors, and your car does not lose any kinetic energy because you just keep sliding right along. Okay, and we've all had that experience, or you will eventually. Okay, have that experience. So we are still reliant a little bit on the friction between the tires and the road, but it's the same thing. It's going to turn your kinetic energy into heat and sound and light. Okay, everyone all right with that so far? Okay, so here's what happens if I want to stop. The force that my brakes exert multiplied by the distance it takes me to stop is equal to my change in kinetic energy, which I get by subtracting my initial kinetic energy from my final kinetic energy. Okay, so all we're saying here is this means kinetic energy final minus kinetic energy initial. All right, now, if I'm trying to stop, what is my final kinetic energy? Exactly, 0, right? So this number here is 0, which means I can basically just take all this stuff out and say that the work my brakes have to do is equal to the kinetic energy I have when I start applying them. Everyone okay with that idea? All right. So that means I can calculate the stopping distance of my car as long as I know three things: the mass of my car, the speed I'm going, and the force my brakes can exert, or the force of friction that is present in trying to stop. All right, so if I wanted to solve for D, what would I have to do with F? Divide it over to the other side, right? Right now I'm multiplying F times D. So I could calculate my stopping distance by taking my kinetic energy and dividing it by the force that's trying to stop. All right, so let's say we know these numbers. Let's say that we're talking about my truck. And we'll say it has a mass of 2,500 kilograms. Okay? And we'll say that the braking force, or the force of friction that is present and able to try and stop my truck, is 9,000 newtons. Okay? The units for force, by the way, are newtons. That's not their true units. It's kilogram meters per second squared, but you're never going to have to know that in this course. Okay? All right, so now I know mass, and I know the force. Okay? Let's say I'm driving through a playground zone, and I'm going the speed limit, because I do that. Okay? So I'd be moving at 8.3 meters per second. That's 30 kilometers per hour. Okay, I've just done the conversion for you. All right. Could I calculate how far I'll travel before I stop? I now know M, V, and F. Can I fill them in? Okay. So let's say I fill them in for me being a responsible driver who is going the speed limit through a playground zone. 1/2 times 2,500 times 8.3 squared divided by 9,000. So all I've done is substitute those numbers into this formula. Okay. That's a long way. I'm going to travel 9.57 meters before I stop. That's pretty much the length of this classroom before I stop. And that's going the speed limit. Now, that number for friction might be a little bit low. Okay? The force of friction stopping my truck is probably a lot higher than that, but I just picked a number out of my head. Okay? Now, I want to show you the effect of speed on stopping distance here. Okay? Your kinetic energy is going to increase exponentially as you increase your speed. Okay? So, let's say someone steals my truck, because it wouldn't be me, and they travel through the playground zone at 60 kilometers per hour, twice the legal speed limit. Okay? How much more kinetic energy are they going to have? 4 times as much, because the relationship between speed and kinetic energy is exponential. I have double the amount of speed, but that number is squared. What's 2 squared? 4. Okay, so it doesn't double my stopping distance, it's going to quadruple it. Okay, is that a big deal? 40 meters to stop, that's half the length of one of the straights on the track out back. That's probably a quarter of the playground zone. Okay, if a kid runs out in the street, they haven't got a chance. Okay, I'm never going to get stopped in time. Actually, it's not me, because we just said I would never do this. Go 60 through a playground zone. That's insanity. Okay, so in this one here, we had 9.57 meters. Okay, if I do that exact same calculation for someone going twice the speed limit, so we'll have 1/2 times the same mass, same vehicle, okay, but now going 16.6, that's 60 kilometers per hour, okay, divided by same amount of force. These numbers don't change. It's the same truck, and it's the same amount of stopping force. Is that as predicted? That's 4 times the previous number. Okay. This is something that for some reason they don't teach you in driver's ed, and they should. The relationship between speed and stopping distance is exponential. Any, even small increase in speed is going to exponentially affect how far it will take you to stop. Okay? And I say that because we don't think about it all the time. Like, for example, it's very common for people to go 10 kilometers an hour over the speed limit. Okay, I'll admit, I do it everywhere except school zones and playground zones. Okay, I'm kind of bad for that. It's like, it's only 10 kilometers an hour. But it isn't. It's actually a lot more than that. Not in terms of it's not 10 kilometers an hour. It's in terms of it's not linear. If I've increased my speed by 25%, I don't increase my stopping distance by 25%. I increase it 100%. Okay? It's going to have a huge effect, okay, on them. So for example, this is 60. Let's say we do this for 40. Okay? 40 kilometers an hour is 11.1 meters per second. Okay, so I increased my speed by 10 kilometers an hour. I went from 30 to 40. My stopping distance went from 9.5 to 17. Almost double. Okay, and that, I didn't increase my speed by that much. Okay, but that's the difference in a playground zone between stopping in time and not stopping in time. Okay. That's the difference between me going home and having dinner with my kid or planning his funeral. That's life. That's physics. That's what we have to keep in mind when we say that 10 kilometers an hour is so important to me. Okay? Because here's what it comes down to, guys. Simple calculation for you. How much time do I save going through a playground zone 10 kilometers an hour over the speed limit? Okay? The average playground zone is about 200 meters long. Okay? Maybe 300. We'll say 250 just to be in the middle. Okay? So, if I want to calculate how long it takes, I take the distance and I divide it by the speed. If I go the speed limit through the playground zone, it'll take me 30 seconds. If I go 40, it'll take me 22 seconds. 22 and a half. I'll save 7.5 seconds. If that's the difference between you being on time or late, you should leave earlier. Okay? You're going to save yourself 7.5 seconds. So, this is the hard lesson. If you hit a kid, because you couldn't stop in time, because you went 40, you are saying that 7.5 seconds is more important than that person's life. Harsh. True. You can't change the laws of physics. That's what happens when you go faster. It takes you exponentially longer to stop. You can't do anything about that. Okay? What you can change is whether you do that at all. Okay? If you go 8.3, that's better. Go 11.1, know it's going to take you twice as far to stop. Okay? If for some reason you go 16, well, you shouldn't have a license. Because that's crazy and irresponsible. Okay? Think about that. Also, don't be distracted. Because that worsens the situation. I think we did that, right? When I did with the ruler? Yeah. Okay? So don't be distracted. If you're distracted, that situation gets worse. Okay? Because then you factor in your reaction time as well. Okay? Big deal. Speed, exponentially related to energy. Mass is not. Okay? If I doubled the mass, it would only take me twice as far to stop. Okay? But I double the speed, it takes me 4 times as much. Okay? So it's a big deal. It's something to think about. Rant over. All right, so thermal energy is a little bit different. Okay, that's kinetic energy, but it has to do with the movement of particles. We're dealing with mechanical energy, which is whole objects. Okay, so the kinetic energy of an object is it's related to its mass and its speed. Okay, we know that that relationship is exponential. Okay, and we still get joules when we do this calculation. Okay, we looked yesterday at what the units for joules actually were, and it was a kilogram meter squared per second squared. Okay, and we still get that when we multiply these things together, because mass is in kilograms, speed squared is meters per second. Square it, and you got meters squared per second squared, so you still get joules. Okay, when you do that calculation. Okay. Oh, see, I had that on there already. All right. I would like you guys to copy this one down, and we're going to walk through it. This is a fairly basic work energy theorem question. In this question, we have a rubber band that's stretched 0.85 meters. What does meters usually measure? Okay, centimeters also measure this. I'm thinking of what would I usually put beside it if I was looking at like V equals D over T. Meters would measure distance. Okay, so anything in meters is going to be a distance. So the question just gave me this. They gave me D. And it says by a force of 60 newtons. Okay, so force is F. Okay, at what speed would it propel a 0.125 kilogram ball? So speed is usually V, and that's probably VF if I'm thinking about the context of this question. And what is this number? Mass. So without even looking at the context of the question, those are the three things the question gave me. Okay, now let's look at the context of the question. A rubber band is pulled backwards by a force. What have I done if I have stretched a rubber band?
You've done work.
I've done work. Okay, I've exerted a force through a distance. I have put elastic potential energy into that rubber band. Okay, that's part of what I have to get from the context of this question. Because I know that, I know this is a work energy theorem question and not a V equals D over T question or an acceleration question. Because I look at the context and I go, oh, that's what's happening here. Work's being done. This is about energy and work. Okay, now it's asking me what speed it would propel it at. So now I have to think of the other part of this. If I pull the rubber band back and I put a ball in it, okay, when I let it go, what kind of energy is going to change for it? What kind of energy has to do with speed? We just talked about it. Speed has to do with, starts with K, kinetic energy. Right? So in this question, the work that's being done is changing the kinetic energy of the object. Okay? That's what I have to get from the context of the question. First, that work is being done, and secondly, that work is changing the speed and thus the kinetic energy of the mass or the object involved. Okay? That's the reading comp part of a physics problem. Okay? Now, do I have a formula that calculates work? What two things do I multiply together to get work? Force and distance. Okay. And how do I usually calculate change? What does delta mean? I'm going to subtract things. What two things am I going to subtract?
Final energy and initial energy.
Final energy and initial energy. Okay. So my final kinetic energy minus my initial kinetic energy. Okay, now here's another spot where I have to think about and visualize what's happening in this question. I have a ball and a rubber band, I pull the rubber band back, and I haven't let it go. There's elastic potential energy in the rubber band here, but is there any kinetic energy yet? No, the ball isn't moving yet. So what's its initial kinetic energy if it's not moving? Right. So I know right now this number, given the context of the question, is 0 and thus unimportant. Okay. So now I'm down to this. Force times distance equals my final kinetic energy. The speed that the ball will leave the rubber band at is dependent on that. So then I can say this. Do I have a formula that solves for kinetic energy? This one? Is this just like what we just did? It's just like the playground zone braking question. Okay? Because both involve a change in kinetic energy. All right, so we're looking for the speed. So I need to get VF by itself. What am I going to do with the half and the m to move them over? Divide, yeah, because right now I'm multiplying them, right? Okay, that solves for VF squared. What do I want? Do I want the number squared or do I want it normal? Normal, so how do I get that? Square rooted. Okay, so this is about as tricky as one of these gets. Okay, so I would have the square root of all of that. That'll give me V. Okay, now I know, right now you're looking at this and going, oh my God, I have no idea what he's doing. Don't worry, we spend lots of time on this. And here's the good news. They're patterned. Once you learn the pattern, they're all the same. Okay? All right, so now I'm going to plug in my numbers. They told me the force was 60 newtons. They told me the distance was 0.85 meters. And I know the mass. Good. Punch that into my calculator. Now, my recommendation here when you start getting to a formula that looks like this by the time you're done, don't try and enter it all in one step. You'll inevitably make a mistake somewhere and then get the wrong answer. Okay, so what I do is I just do it piece by piece. 60 times 0.85. All right, I'm going to divide that number by half of this number. And then I'm going to square root that number. Okay, so that ball is going to leave the rubber band at 28.6 meters per second. This is why your elementary school teacher told you not to play with a slingshot or put a paper clip in a rubber band or any of those other terrible ideas that kids do. Okay, because they can go very fast. Take out someone's eye. Okay, everybody with me on how that one works?
Is there a difference between questions? How like there's a difference between vector and
in this case, it asked how fast, so it was only asking for speed. And we don't care so much about direction when we're dealing with energy, because energy is scalar. Yeah, so that's a good question. So vectors are less important. Okay, so what we had to do to solve that question was first identify that work was being done. The second thing we had to do was identify what kind of energy the work was changing. In this case, it was kinetic. Then we wrote down our givens and established a formula that work was equal to the change in kinetic energy. We filled in the formulas, manipulated, and solved. That's the pattern. Okay? The pattern is find out if work is being done. Find out what kind of energy is changing. Set it up, manipulate, solve. Okay? The pattern is always going to be the same. The trick is being able to figure out if work is being done and what kind of energy is changing. That's actually the trickiest part. I trust your algebra. Okay? I know you guys can do these kinds of manipulations. Okay? That part never worries me. Okay? The part that's difficult is the contextual part, reading the question and getting what I need from it. okay? Like, right up until physics 30, we see that that is usually the most challenging thing for people, okay? It's not the math. The challenging part is getting to the math. Okay, this one is similar. Write this one down and give it a try. I'm going to have you guys see if you can solve it first before we go through it together. So, your givens for this question are that you know the mass of the rock, 550 kilograms. Okay? And you know that it goes from rest to 4 meters per second over a distance of 25 meters. What force is exerted? All right. So they make it sound a little bit like an acceleration question. Would you agree? They give me initial and final velocities, or speeds in this case. How do I know it's not an acceleration question?
You got mass?
I got mass, which is never part of an acceleration question, and I'm asked to calculate force, which is also not part of an acceleration question. I know I can't use A equals VF minus VI over T. I don't have A or T. Okay, I can't use that formula. All right, so now the next thing I gotta ask myself is, force and distance are usually in what kind of a problem? A work problem. Is work being done in this question? How do I know?
Pushes.
Yeah, it talks about pushing, and it talks about a change in speed. If there's a change in speed, what kind of energy is the work changing? Kinetic. Speed has to do with kinetic energy. That's what I have to get from the context of this question. I know the object's being pushed. I know it's being accelerated. Acceleration means the speed is changing, and a change in speed means there's a change in kinetic energy. Okay, so then I can do this. All right, see if you can take it from there. Do I have a formula that calculates work? What two things do I multiply together to get work? Force and distance, okay. And change in anything is final minus initial, okay? So that's going to be my final kinetic energy minus my initial kinetic energy. Right? If I look at this question, it tells me that initially the rock isn't moving. So how much initial kinetic energy can it have? 0. It's not moving. It doesn't have anything. And that's because I would go 1/2 times 550 times 0. Okay, well, anything times 0 is 0, so that means this part here is irrelevant. Okay, and we're back to this. The final kinetic energy equals force times distance. They want to know what force. So how do we get force by itself? Divide by distance. So I leave force over here. Okay? And I saw that a lot of people had that. Okay, so now here's where people I think got a little bit confused. Some people. Okay, 1/2 mvf squared divided by d is going to give me force. Now, I had a lot of people who had this. They got the right answer. But I had a few people who did this because they saw it in one of the other questions. Do I need the square root in this case? I don't, because force isn't squared. I would only need the square root if I was solving for v. Okay, so I don't need the square root here. Okay, this will solve for f. So I'm going to have 1/2 times the mass of the rock, 550, times the speed of the rock, squared. That part is squared. Okay, and then I divide that by the distance, 25 meters. All right, so 0.5 times 550 times 4 squared divided by 25. Okay, so I get 176 newtons. force being exerted. Okay, everybody all right with that? Okay, are these fairly, did I lose you something?
Oh, no, yeah, no.
Are these pretty patterned? Like, so far, every question has started out with pretty much the same stuff. Okay, work equals a change in kinetic energy. Work equals a change in kinetic energy. Work is a change in energy. Okay, like they all start that way. The only challenge is figuring out what kind of energy is changing. The first few we've done, it involved kinetic. How would a change in potential energy be different? Instead of speed changing, what would change for something changing its potential energy?
Distance.
Close. A vertical distance is called a height. Yeah. And if I lift something, then I'd be changing its potential energy. Okay? So all I have to do is in the question look at, is it being lifted or accelerated? Okay? And then I'd be able to tell. If it's accelerated, it's a change in kinetic energy. If it's being lifted or lowered, okay, but a change in height, then it's potential energy. All right? So on that note, let's try this one. Because it's a potential energy question instead. And it's actually a little bit easier because it's only asking you for the work, not force or distance or anything else. Okay, so a mail carrier picks up a 10-kilogram package. What did they just give me? Mass. Okay, so we know the mass. 10 kilograms. Okay. On the 3rd floor of a building, which is 30 meters above the ground. Then they deliver it to the 10th floor, which is 100 meters above the ground. What are those two numbers? Height. Yeah. So my initial height is 30 meters, and my final height is 100 meters. Okay. How much work is done? All right. There's no mention of changing the speed of the package, is there? Right? There's no speeds given in here. Since there's no speeds and a change in height, I have to assume that the work being done is changing what kind of energy? Not kinetic this time, it's potential. Okay? I know it's potential because it's getting higher off the ground, and it takes work to lift something. Okay? So I can say here then that the work being done is causing a change in potential energy. Right? And this question only asks for the work. There's only two ways to get work. Force times distance and final energy minus initial energy. I don't have force or distance here, do I? I mean, I could calculate the distance, it's 70 meters, but I don't have a force, so I can't do that way. But I can do this. Work would equal my final potential minus my initial potential. How do I know I can do that one? Do I have a formula that calculates potential energy? I do. I have this formula. And I have those numbers. They told me the mass is 10 kilograms. This is on Earth, so it's 9.81 for G. And I know the initial and final heights of the package. So I can say then that the work is going to equal m times g times h final, that would be my final potential energy, minus m times g times h initial. Okay? This time, my initial isn't 0 because I start above the ground already. So now, all I have to do is plug in the numbers. I don't even have to manipulate anything. I'm just looking for the amount of work being done. Okay, so I just punch in the mass, 10 kilograms, times g, 9.81, times my final height. I took it to 100 meters. And then I subtract 10 kilograms times 9.81 times the height I started from, 30 meters. Okay, that will calculate the change in energy, which is, after all, what work does. So that person does 6,867 joules worth of work. Okay. Was the pattern on this one still very similar to the pattern on the other ones? Any? Still started out with works of change in energy. The only thing that was different was this time the energy was potential. I still went final minus initial. The only difference was this time it was potential instead of kinetic. Okay, then I just plugged in my numbers and solved. I didn't even have to manipulate for this one. Now, I could have changed that and told you that they did 6,867 joules worth of work and asked you for the final height. And you would have had to manipulate a little bit instead. Okay? But they all work pretty much the same. Those first few steps are always going to be the same. Okay? The challenge is, can I read this question and get what I need to from it? Okay? All right. Okay, give that one a try. That's the answer, so you'll know if you did it right or not. Okay, and then maybe we'll call it a day after that one. Okay, so let's have a look at this one here first. So the thing it tells us is the bulldozer does 7,500 joules worth of work. So they told us work is 7,500 joules. Okay, and it says it pushes a truck from a speed of 2 meters per second to an unknown velocity. That means the 2 meters per second is which v? Initial, yeah, because that's what it starts at. Okay, so 2.0 meters per second, and that means that Vf is unknown, and what we're solving for. The truck has a mass of 2,500 kilograms. Okay, what is its final velocity? Okay, is work being done? Yes, they told me how much. They told me 7,500 joules. Okay, so I know work is definitely being done. What kind of energy is it changing about the truck? The kinetic. How do I know that? Because it's speeding up. And speed has to do with kinetic energy. All right, so I'm going to expand that out. Okay, and I'm going to say that that means final kinetic minus initial kinetic. Okay. What I'm looking for is part of the final kinetic energy. Would you agree? Okay, so can I move the kinetic energy initial over to the other side right now before I expand? I can, or I can do it after I expand. It doesn't matter which way you do it. I just like doing it before I've got 1/2 mv squareds in there. All right, so I'm going to add the initial kinetic energy over to this side. Okay. Now I'm going to plug in my formulas. 7,500 joules plus 1/2 mv initial squared equals 1/2 mv final squared. All right, can I get v final by itself? Where did I lose it?
Why do you divide by 2 and square, or halves, or in square, MVI?
Because the 1/2 is there to make sure you're getting the average number. Okay, it's kind of the best way I can describe that. They're not related to each other.
Okay.
Yeah. Okay, so the half has to stay in, the square has, because 1/2 and squaring are not the same thing, right? Okay, I want to get VF by itself. So what do I do with the half and the m? Divide, because I'm multiplying them right now. Okay, so that half of m will come over here. That gets VF squared. What do I want? Just VF. So what do I have to do to this whole thing? Square root. Okay, so that means then that VF will be the square root of 7,500 minus 1/2 times 2,500 kilograms times 2 squared, the initial speed of the truck, divided by 1/2 times 2,500. Right, if I do that, I should get 3.16 meters per second. And in my calculator, it looks like this. 7,500 minus 0.5 times 2,500 times 2 squared, okay, divided by 0.5 0.5 times 2500. And then square root that. Whoop. I messed something up. Screwed up something somewhere. Should have come out to 10.
1/2.
Oh, yeah, I subtracted up here. Yep, that's exactly what it was. Okay, sorry guys, I messed that up. 7,500 plus. Oh, come on. That's better. Okay. And then divided by, and that's got to be in brackets. Okay, that gives me 10. Square root of 10 is 3.16. Boy, see, something simple like forgetting to add and subtracting makes a big difference. Okay. All right, we're going to keep working on that for a while. Okay, but just I'm hoping that you're seeing that there's always a pattern to these, right? Like the first 3 or 4 things I do in every question is the same. Right? The challenge is, what do I need and what am I given? Okay? What kind of energy is changing? That's the challenge. Get that from the question. Okay, good enough for today.